at the tables in Appendix E very shortly. That's at the very end of the book, just before the glossary and index. First of all, present value is the value of an amount or amounts received in the future at today's value. So we're going to take a look at examples. And in this case, they're giving you a very simple example. It says if you invest $1,000 today at 10%, you'll have $1,100 in 1 year. In contrast, if you receive $1,000 1 year from today, you will actually lose $100 in interest because the present value would be less than the future value of the $1,000 that you would receive. So we'll take a look at how these are calculated. What you need to understand is that the present value is always less than the future value. And again, they give you a little example. And before I forget, on the Canvas webpage, under Chapter 9, I've given you some examples of business-related present and future value problems and the solutions. So you might want to play around with those and take a look at them. But we'll also be looking at some examples here. So let's take a look at present value of a single amount. Present value of a single amount is computed by taking the known future value and multiplying it times 1 divided by 1 plus I to the nth. Or what we're doing is taking the reciprocal of the future value and multiplying it times that future value to get a present value. So let's look at an example. It says, assume that today is January 1st, 2016, and you need to make a $1,000 cash payment on December 31st, 2018. So you can see that that would be the end of 2016, the end of 2017, and the end of 2018. So that would be 3 years from now, January 1st. At an interest rate of 10%, how much would you need to deposit today to have it equal exactly $1,000 on December 31st, 2018? You could discount the amount year by year to figure out how much you would need to deposit today, but it's easier to use Appendix E. So let's go to Appendix E, and let's go to present value of $1. This is also called present value of a single sum. Notice that it goes from periods 1 to 10 and 11 to 30, and the upper tier here goes from 1% to 7%. The second tier down here goes from 8% to 25% and years 1 through 30. So if we go back to the example, they said that the interest rate is 10% for 3 time periods. So what we're going to do is we're going to come to the 10%, which is here, and we're going to come to 3 years, which is here. And we can see that the present value of a single sum is 0.75131. A lot of tables round it to just 3 places or 4 places, so it's up to you. Remember, most of the time these are estimates anyway that we're dealing with. But in this case, we would take this present value of a single sum factor and multiply it times the $1,000 to discount it to the amount we would have to put away now in order to have $1,000 at the end of year 3. So here it shows you that when we multiply this factor times the 1,000, it gives us the present value of $751.31. So that's the amount we would have to put away right now. This diagram is very helpful because it shows you that if we deposit $751.31, at the end of the first year, at 10%, we would increase the amount in our account by $75.14, bringing the value in the account to $826.45. At the end of the second year, interest would then be 10% of the original principal plus the first year accrued interest. So if you take 10% of 826.45, the interest in year 2 is higher than what it was in year 1. And when we add the 82.64 onto the amount that was on deposit at the beginning of year 2, it gives us the amount on deposit at the beginning of period 3. Again, at 10% interest, the interest in year 3 will be higher than it was in years 1 and 2. So you can see that compound interest always calculates the interest on not just the original deposit, but on all the accumulation of interest. So what you're going to see is when you are lending money, compound interest is good because you're earning interest at a higher and higher rate. But if you're the borrower, compound interest means that you're paying significantly higher interest because the principal is coming down at a slower rate. So that's why when you look at mortgages and you look at a 30-year mortgage versus a 15-year mortgage, if you sign a mortgage note for $400,000, you're paying almost all interest initially until that debt comes down. And it's only in the last several years that you're paying off primarily principal and less in interest. When we talk about present value of a single sum or present value of $1 versus present value of an annuity, in the prior example, it was present value of a single sum because we're going to make one payment in 3 years of $1,000, and we're going to make a single deposit now that we determine $751.31. That deposit will then increase to the $1,000 as the result of compound interest, but it's a single deposit, single withdrawal at the end. When we have an annuity, it means there is a series of consecutive payments or deposits, and those payments or deposits have to be an equal amount each year in order to use the annuity table. And the interest period or have to be of equal length, so it has to be every year or every 6 months or every 3 months or every month, and it has to be the same interest rate each period. But if these exist, then we can use the annuity table instead of having to calculate the present value of each future amount and then summing it up. But if we had 3 amounts that we expected to come in, and the first year we expect $10,000 to come in, the next year we expect $30,000, and the third year $50,000, we would not be able to use the annuity table. We would have to calculate present value of a single sum for the $10,000 coming in year 1, present value of a single sum for n equals 2 at the interest rate for the $30,000, and present value where n equals 3 at the interest rate for the $50,000. But if the amount coming in or going out each period is the same amount, and we can shortcut. So this is showing you what I was just talking about. We could go to the present value of a single sum table and look up n equals 1 at the interest rate of 10% and get the factor, multiply it times the $1,000 to get the 909, and then look up n equals 2 at 10%, get that factor times 1,000 to get 826.45, and then where n equals 3 at 10%, we get this factor, we multiply it times 1,000 to get the 751, and we would sum up all the individual present values. But we have a present value of an annuity table that shortcuts this process. And what it does is it takes the amount of the present value factors and sums it. So if you were to add these 3 factors together, it would equal this 2.48685. So let's go to the annuity table. So this is present value of a single sum. The next one on the next page is set up the same way as what we saw. It's present value of an annuity. And you can see that we've got time periods 10 through 30. It goes out to 7%. And then the second grouping is for 30 years, and it picks up at 8% and goes out to 25%. So here are the factors, okay? for n equals 1, n equals 2, and n equals 3. So if we go to n equals 3 at 10%, notice it pulls that accumulated figure, which would be the same as using the present value of a single sum, where we would add and combine those three amounts. So the shortcut is to use the annuity table if the amount is the same, if the interest is the same, and the length of the period is the same for each deposit or each payment. So in this example, they give you an illustration of an annuity over time. So let's take a look. As shown in Exhibit 9.3 down here, if you deposit $2,486.85 today at an interest rate of 10%, that amount would grow to $2,735.54 after the first year, because we would earn interest of 10% on that amount. So then the balance would increase to the $2,735.54. At that point, you would make another payment and have $1,735.54 left. And so what happens is it goes up by the amount of interest and down by the $1,000 payment that you make each year. Then in year 2, the $1,735.54 would increase to $1,909, which is the interest incurred, and then it would decrease by the second payment of $1,000 down to $909. And then finally, it would increase by interest of $90.91. And when you make the final and third payment, it would wipe out the amount that you owe. So you can see that that's what this table does. So what it's showing you is if you have an amount that you have to pay in an annuity stream of $1,000 each year for 3 years, the amount of the present value of that annuity would increase by the amount of the interest and then decrease by the amount of the payment each year until at the end of the third year, your obligation is paid. Let's take a look at some accounting applications of present value. They tell you on January 1st, 2016 that we bought some new delivery trucks and we signed a note and agreed to pay $200,000 on December 31st. Now, notice that this is 2 years from when we buy the delivery trucks. And this is a non-interest-bearing note because no interest payments are required over the life of the note, but instead the interest is built into the principal of the note, and we will repay the $200,000. So the question becomes, is the delivery trucks equal to $200,000, or because interest is built in, and we saw in Chapter 8 that we cannot capitalize interest on purchased assets. So, do we have to remove the interest from the $200,000 face value of the note that we're going to repay in 2 years? And the answer is yes. And the way we would do that, and I recommend using these types of number lines, it just helps you tremendously to see that you're going to make a payment of $200,000 on December 31st, 2017. And now the question becomes, how much will you record this asset on the books at and the liability? Well, the answer is if the interest rate is 12% and the note is going to be repaid at the end of 2 years, and it's being repaid in one lump sum, that makes it present value of a single sum, which was the first table that we looked at. And so we would go to n equals 2 at an interest rate of 12%. We would pull the factor from the table, and then we would multiply that factor times the $200,000 to discount it to its present value. So let's go to the table. Let's go to present value of $1. Let's go to 12% time period 2. You can see that it's 0.79719. And remember, this is present value of a single sum. So when we take that 0.79719 and multiply it times 200,000, we get this $159,438. So on January 1st, 2016, we would debit the asset delivery trucks for the present value of what we will repay at the end of 2 years, and we will put the note payable on at that amount. At the end of the first year, which is December 31st, 2016, the value of the note, the face, is going to increase by the amount of interest expense that has now been incurred but won't be paid until the end of the second year. So what we do to calculate interest expense is to take the 12% times the $159,438, which is the amount of the note at the beginning of the first year. That then gives us interest expense at the end of year 1. When we debit interest expense, since we're not paying for it, it's going to increase the note payable by the same $19,133. So what happens is the liability increases from $159,438. It will increase by the $19,133, and so it'll be $178,571. And that $178,571, when multiplied by 12% at the end of year 2, will compute interest expense of $21,429. Again, we will debit interest expense and credit notes payable for that amount. When we add the $21,429 to the $178,571, now the note payable equals $200,000, which is the amount that we have to pay. So right after we do the calculation of interest and increase the note, we're going to pay off the note in the amount of $200,000. So now the note payable is debited to reduce it, and cash goes out in the amount of $200,000. We report the interest over a 2-year period on the income statement, $19,133 in the first year and $21,439. On the balance sheet at the end of the first year, we would show notes payable of $178,571. Here's another example. It says on January 1st, 2016, Starbucks bought several new espresso machines. The company elected to finance the purchase with a note payable to be paid off in 3 annual payments of $163,685. Each payment includes principal plus interest on the unpaid balance at 11% per year. The annual payments are due on December 31st, 2016, 17, and 18. So again, using that diagram, it helps us see that we're going to make payments beginning 1 year from when we buy the new espresso machines. So what we would want to do, since this is multiple amounts in the future, this is present value of an annuity, where n equals 3 equal payments, and the interest rate is 11%. So we would go to table E2, which is present value of an annuity. So, oops, sorry about that. Present value of an annuity, and we would go to 11%, and we would go to time period 3, because we're making 3 payments, and the factor is 2.44371. We would come back and we would multiply that times the individual annual payments. So the individual annual payment of $163,685 times the present value of an annuity factor, where n equals 3 and the interest rate is 11%, would give us approximately $400,000. At this point in time, we would put the value of the espresso machines on the books at $399,999, approximately $400,000, and we would show the note that we owe equaling approximately $400,000. At the end of the first year, when we make the first payment of $163,685, part of this is interest and part of it is the reduction of the note. In order to calculate the interest, we have to take the principal of the note at the start of year 1 times the 11% to get $44,000. Then we subtract the $44,000 from the $163,685, and the remainder of the payment has to equal the reduction to notes payable. So then the reduction to the note would be deducted from the $399,999, and that would be the amount that would be still outstanding for the obligation at the end of year one. To calculate the amount of interest at the end of year two, we would take the remaining note payable, which in this case is now $283,14, which would be the $399,999 reduced by the $119,685 by the 11% to get $30,385. That interest is then deducted from payment number two to get the amount that we reduce notes payable by. Finally, because the note has dropped again, now to $147,464, when we multiply it times 11%, the interest in year three is much less than it was in year one and year two. We end up deducting the $16,221 from the cash payment, and that shows that we're going to pay off the remaining balance of the note. So the note at the end of year three would equal zero. So they show you some other examples here, and I'm going to let you go through them. But what I do want you to know is we also have future value tables, and let me just show you those. So we have table E3, which is future value of $1. We know that the future value always has to be greater than the present value. So what I want you to notice is that every factor on the future value of a single sum table has to be greater than 1, because 1 equals the amount of the present value, and since the future value has to be greater than the present value, the factor always has to be greater than 1. Let's do something just out of curiosity. Let's go to 10% for 3 years, because we used this present value factor where n equals 3 and the interest rate was 10%. If you remember, the formula said if we take 1 divided by the future value factor, 1.331, we end up with 0.751315. Well, if we go all the way back to the present value of $1 table, we go to 10%, okay, and we go to time period 3, you will see that we have 0.75131. So table 1 and table 3 are mathematical reciprocals of each other. However, caution, present value of an annuity is not the exact mathematical reciprocal of table 4, which is future value of an annuity. And that's because the present value of an annuity includes the same number of compounding periods to compute interest as the number of payments. So if you're going to make 6 payments, included in the factor is 6 compoundings of interest. However, table 4, which is future value of an annuity, the assumption is made that after the last deposit or payment at the end of, say, year 6 is made, there is not a 6th compounding of interest. So therefore, when you use n equals 6 on the future value table, you're really only involved with 5 compoundings of interest. So the tables are not reciprocals of each other. So you need to know whether you should be using future value or present value, especially when it comes to annuities, because those factors are not mathematical reciprocals.